Hello, everybody. Hey. So today we're going to be talking about isomorphic reasoning and about counting polymorphic type inhabitants, but really about counting types. And I would just like to say that this topic in particular is probably one of my favorite topics in functional programming. You learn a lot of stuff about functors, monads, applicatives, and so on, but all of that is kind of like, it's just like abstractions on top of a type system. But what about the type system itself? And what about, like all of those like different things that you can imagine, functors abstract over one function, right? fmap. But how many functions you can come up with? There are a lot of possibilities there. And so, in some sense, this is more talk of not just about functional programming, but about type systems, about lambda calculus, about category theory, and about isomorphic reasoning. Isomorphisms play a huge role. Okay, and let's go to the next one. So let's start with just introductions. My name is Alexander Konovalov, and I work at a company called Compellin. We're a small startup that does, you could say, I guess, artificial intelligence, data science, that kind of thing. And I've been mostly doing Scala, although obviously, like everybody who gets into functional programming eventually learns Haskell. And like nowadays I'm looking towards sort of hoping to transition, like over time maybe at work to more Haskell and less Scala. But I still have a lot of, love for Scala, nevertheless.
Yeah. So I got mine right here.
Okay.
Sure. My name is Pillmore. I am a Haskell engineer with Yoneda, a blockchain company based out of Brooklyn, which does its own smart contract language. And we are entirely in Haskell, which is fantastic. Yeah, okay. Yeah, so I got my start in Scala as well with functional programming around 3.5 years ago. And I found that it was a very interesting connection to category theory, which I had learned in my undergraduate. And I met Alex through my work with Scala, where we happened to maintain the same project. And it was a very sort of deep dive into functional programming concepts in Haskell embedded in Scala. So this talk is kind of a culmination of years of work and understanding from several different points of view, including type systems, including set theory, including basic arithmetic, which I hope we all know, and category theory. So yeah, I'm happy to be here and to give this talk with Alex. I'll be handling the category theory of things mostly as we dive into it. And Alex was kind enough to actually write out most of the exercises, which we're going to go through in his amazing blog post, which we'll link everyone to during the exercises.
Now, there's also a Slack channel, which we just created, so it's completely empty. It's isomorphic reasoning at LambdaConf.
Great. And you can feel free to ask questions whenever we're going through this. Whoever is speaking probably won't answer the questions, but whoever is on the computer can look from time to time and make sure that we can answer your questions as we go along. And I'll just have my phone up for that. Oh yeah. Where should we put it?
Oh.
Here's on top. Okay.
Okay, so why this workshop? Well, in this workshop you're going to learn a lot of category theory, lambda calculus, although not exactly lambda calculus, but more like types in system F and system F omega. right? We're not going to be writing a lot of lambda terms, but we're going to be writing a lot of types of those lambda terms, right? You're going to learn about powerful techniques to think about types, right? And to think about how can you write a program and then evolve it and transform it, and how to see through how to see the connections between different techniques and different buzzwords, like perhaps free MTL, or say recursion schemes, and final tagless. All of those techniques are basically the same exact thing. It's just you have to be able to see those connections. Actually, can we go back? And everybody knows that this type, right, for all A to A has only one inhabitant. But how do we know that? I mean, you can say that, well, syntactically there is only one way to construct a function, but how do we know that, right? And so in this talk we're going to actually prove that this type has only one inhabitant.
Is it possible to access the slides now?
Yes, we do have a GitHub link.
Can you just post it onto the Slack?
Yeah, so it'll just be the main PDF of this repository.
It's in our Slack channel. Isomorphic reasoning at LambdaConf 2019. Yeah.
So when you say A to A, that's functions that actually terminate, right?
Yes. We are going to be dealing only with terminating functions here.
Assume Haskell, whenever we write Haskell, is living in that moral subset without bottom. Okay. And all coproducts exist. So we have all ithers, and nested ithers.
Mm-hmm. And we are also going to talk about free theorems just a little bit, and we'll see that there is a much easier way to think about free theorems than the actual free theorems that you can derive. All right. And as I said, there is a lot of hype about functional programming techniques, but in reality, a lot of those functional programming techniques are exactly the same thing. So we'll see, maybe not exactly that, but you'll sort of learn the techniques that will allow you to see these connections. And now, why do we want to count type inhabitants? Well, let's say that you are a compiler writer, and you know that a particular type has only one inhabitant, right? So, for example, this often occurs in dependently typed languages where you have proofs. Proofs normally have only one type inhabitant. And if you have a complex proof, you don't really need to run all of that code. Has anyone in the audience written a proved, let's say, commutativity of natural numbers in Agda or Idris or any other dependently typed languages? Right, so you know that in those languages, the way you prove things is you recursively deconstruct your arguments in order to build up a proof. Well, all of that computation doesn't really do anything, because at the end of the day, you know that there's only one proof, because all proofs are identical. And IDE writers can also benefit from this technique, because if you can enumerate things, you can likely, if you can count things, you can likely enumerate them as well, which means that you can have a very powerful auto-completion technique where you write your type and you get all possible inhabitants up to observational equivalence, which means that all of those type inhabitants are going to differ in some very fundamental way. They're going to be distinguishable. However, there are not going to be any duplicates. And if you have a function that, say, takes a type that doesn't have any inhabitants, then you can just dismiss it outright instead of actually proving first that that type doesn't have type inhabitants. So it's kind of like a proving technique as well. Furthermore, if you prove that a type is inhabited, then you also prove that the corresponding theorem is true. If you are familiar with Curry-Howard isomorphic or correspondence, right, you know that every program, or rather the type of every program, corresponds to a statement in logic. And so when you write a program, you are actually proving things in logic. And finding that a particular type is inhabited is equivalent to proving that rather, if you can find a constructive, if you can count a type constructively, then you have proved that theorem constructively. And we had a question over there.
Yeah, if I heard you correctly, I heard that you said that all proofs of the same proposition are equivalent or are identical. I just said identical. And yet here you're saying you can count the different proofs of that type.
We identify them.
Yeah, so if you're familiar with, say, homotopy type theory, right, there not all proofs are equal. And they're actually distinct, like even for equalities, you have multiple different equalities between terms. And so in certain type series, that's not true. You might have let's just say that when you are dealing with propositions, meaning that like actual types that only have one inhabitant, that's like by definition, then you can definitely use this technique, right? Not just by definition, but you can actually, if you count the number of inhabitants, then you can discover whether that number is, whether you have only one inhabitant or not.
So let's say the type bool
Yes.
has two inhabitants.
Yes.
But each one is a proof that bool is inhabited.
Yes, that is correct.
So then we have two different proofs and they're not identical. One.
True. However, if you, let's say, take a term exists x of type bool, you know, there exists essentially if you have a proof of inhabitants does not necessarily need to be, let's say, constructive. You can have a proof of inhabitants that is doubly negated. So, for example, you can have a bool to void. You know, how do I explain it? So you have like a bool to bottom, and that thing, you take that thing, and you again to bottom, right? That's doubly negated bool. And that thing actually has only one inhabitant, and that is a proposition. But it's true that a proof of the form x of type bool is actually, or like the bool itself, right, is not a proposition and has multiple type inhabitants. All right, so what exactly do we mean by counting? Like, what do you think? Let's say, you know, like you have bool, right? There, it's pretty simple. But in general, how do we know that we've counted all possibilities? Like, how do we know that if we, you know, what are some techniques for counting types, let's just say? Let's say I have maybe of bool. How would you go about counting that? Yeah.
So maybe it's the sum of just A and nothing.
Right, so you can sort of like,
Nothing is 1 plus just A, and A is the number of inhabitants of that. So the main pool has 1 plus 2, so there's 3 inhabitants.
right, so essentially what you did, you just counted things, right? I mean, you literally enumerated all possible inhabitants. But in order to enumerate things, you can go ahead. In order to enumerate things, you actually need to be able to distinguish between them. You have to be able to you have to be able to say whether two things are equal or different, because otherwise you cannot count them. Yes?
How about structural induction?
Yes. That is, in some way, it's also enumerating, right? We consider all cases, and then for every case, we, by induction, we continue the process, sort of recursively, right? However, right, so consider this particular question, right? We have three different, are they different, first of all?
Yeah, I don't know.
Right, so we have three expressions here in natural language, let's say. And it turns out that if you actually, if you actually compute the second number and if you find the solution to the third question, right, to the third description, then you'll find that all of them are exactly the same thing, right? The number is the same, but the description is different. So the question is, like, do we distinguish between all three, or do we, like, how do we think about equality exactly in this particular case? Are things equal, or are they different? Now, if do we have a, yeah, okay. So if these two are considered to be expressions, then they are different. How do I know that they are different? And let's go to the next slide. So imagine that I wrote my Haskell type of expressions, and I just wrote both of those in terms of that type, right? Now I can observe the structure. I can see that they're different because the structure of the expression is different. However, if they're integers, if we only look at the values, then they're exactly the same, right? So here, for example, instead of writing them out as expressions, we've lost that information. We sort of like reduced that information down to the value. And so now we can no longer distinguish between them. Oh, and by the way, they do evaluate the same thing, just in case you're still unsure about that. Okay, so it turns out that this way of thinking of things in terms of their properties dates back all the way to 1600, right? And Leibniz. And he came up with this principle, which is called identity of indiscernibles, and also indiscernibility of identicals. These are two principles, but we are going to think of them as just one principle, identity of indiscernibles. And the idea is that if two things are different, then you must be able to find a property that they have in different. And if they are the same, then you'll discover that all of their properties are exactly the same. So we can express that in terms of sort of like a logical expression, where we say that x is the same as y if and only if for all p, where p ranges over all possible properties, p of x is the same as p of y. Now this p, since it's a we can just assume that p of x is just a proposition, so that equivalence is actually sort of like comparison on booleans, and we know how to compare booleans or compare truth values. So going back to our expressions, right? We cannot see the difference between them if we look at them as values in a pure functional programming language. But we can see the difference between them as expressions. And so the main difference is the things that we can see, the things that we can observe about them. And so what we should really care about is our sort of language, or rather the things we can observe in our language and the things we care in our language. So for example, if you care about performance, those two expressions are different. Because one of them, if you care about compilation speed, they're different, right? One of them is just a number, so it's just going to parse, and that's it. The other one is an expression, so it might incur some runtime cost. Perhaps not in this particular case, but if you had a more sophisticated expression, that would incur runtime cost. And so you have to understand that it all depends on the set of those questions that you can ask about your programs. So how does that apply to functional programming? Because we've been talking about some things, just like math and expressions, right? Well, it turns out that it applies directly. Let's go. Okay, so actually, yeah, this slide is not entirely up to date. But nevertheless, I'm going to explain. Well, first of all, let's look at Booleans, right? And let's think about the things that we can observe in our language. What can we observe about Booleans? Well, really, if you're dealing with, say, Haskell, the only things that you can really do with your data types is pattern match on them. And so, and the way you pattern, and what pattern matching allows you to do is to literally compare your data constructor, in this case, two data constructors, true and false. That's the only thing you can observe. And so, if you were to exhaustively enumerate bool, in terms of this equality, in terms of the things that you can observe, you would find that there are only two values, right? True and false. If you have a tuple, well, how do we enumerate tuples? So let's say we have a tuple of type A and type B. One very natural, what can we observe about tuples? The only thing we can observe is the first component and the second component, right? Basically, we can pattern match, and we can extract those components. Now, once we have observed one of the components, if we extract one of the components, the only things we can observe about that component, we will be able to enumerate that. Then we can also enumerate the second component. Now the question is how many combinations are there? Right? It's just, it's going to be the product of both components, of the number of inhabitants of both components. Right? Why is that? Well, let's imagine that we fix the first component with some value, and then we go through all possible values for the second component. Then we fix the first component to some other value and do the same process again, right? And so you would find that for every single value of the first component, you have, of the component A, you have the number of inhabitants of B of possible values. All right, now for isers, it's the same thing, right? What can we observe about isers? Well, we can pattern match. Again, it's like for any data type except functions, that's the only thing you can do, right? And so for iser, we have two possibilities. It's either left or right. That's the first thing that we observe. And then as soon as we see that it's, let's say, left, let's say that it's either A, B, then the left component is A, then we can enumerate that A. And then if we see that it's right, then we can enumerate B, right? And how many possibilities are there in total? Well, first of all, it's either left or right. And then if it's left, then there are A possibilities, and if it's right, then there are B possibilities. So in total, there are A plus B possibilities. Now maybe it's just a partial, it's just a sort of a particular case of either. So we get 1 plus a, whatever is in that maybe, right? Because think of maybe as either a unit or a. Then we have only one possibility for a unit, because you cannot really observe anything about a unit, but you can have one value. And so all values of unit are the same. We cannot see any difference between them. And by the way, if you're dealing with other languages than Haskell, then you might be able to observe some things, like referential equality, in which case all of this breaks down. And you have to ensure that your language is small enough that you can actually make meaningful statements about that. All right, now the hardest one is functions. Do we actually perhaps have, no. Go back. All right, so this slide is unfinished, as you can see, but nevertheless, how do we think about functions? Well, again, let's think in terms of observations. If you have a function from A to B, what can you observe about that function? Well, in order to do anything with it, right, we don't have any, like we cannot compare functions directly. The only things that we can observe about a function, we can pass it an argument, and then we can see what the value it gives back to us, right? Now, when it gives us a value back, there are going to be B possibilities, right? A to B, B possibilities. But that's only after we pass it a value. Now, how many possible ways to pass a value to the function A to B? How many ways do we have? A, right? So for every single one of those, we're going to have B possible values that are returned by that function. Now, so think about a function as a huge table where we have an entry for every single possible value of A, and every single entry has type B. So think of it as a tuple, as a giant tuple. It has, it's basically B, 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 and so on. And the total number of times it is repeated is the number of inhabitants of A. Right? Now, we've talked about tuples, right? And there we had to multiply the two things together. And by the way, there are going to be exercises, I think, hopefully, on this particular topic. And so, you know, we'll go a little bit more through this later. So, as you know, we've discovered, right? When we have a tuple, then we multiply individual components together, right? Well, here we have a giant tuple. So the same idea applies. We multiply them together. Every component has B inhabitants, and there are in total A components. And so for functions, we get B to the power of A. So the number of inhabitants of a function from A to B is B to the power of A.
Question then.
Yeah.
That was the total number of functions from A to B.
Yes. However, I should add that there is a small caveat here. You have to be very careful, very, very careful about polymorphic function types. Like if you have a function that contains a type, an abstract type, all of this, none of this works. Like everything breaks down. And the same thing for isers and so on. So you have to be like polymorphic types. We're going to talk about them, but they're a lot trickier. They're like consider even for all A to A, right? Z function has only one inhabitant, but if we use this logic, we would say, oh, it's A to the power of A. But you know, what is A in this particular case? It's not defined. All right. So far, this. How many people? Could we see some hands? So like, how many people are familiar with you know, just regular enumeration of inhabitants of like simple types like that? Yeah, pretty much everybody, right? Okay, so So far, we've been enumerating just simple types. And we're literally enumerating them. But that is very, it's a powerful technique, but it's kind of, it's not going to get us really far. So we want a more powerful technique. And it turns out that there is one where instead of enumerating things, you use isomorphisms to transform your types. Now, here's an example, right? If we have a Boolean, what we did in essence when we enumerated things is that we have found an isomorphism from Boolean to a set of two elements, right? So in some sense, you can think of natural numbers, and we'll come back to that, as cardinalities of sets. In which case, counting is just finding some way to map your type onto some finite set. So what is an isomorphism? And for now, we're going to talk about isomorphisms in functional programming. Now, an isomorphism is two functions, one from A to B, another one from B to A, such that their composition is an identity in both directions. Now, we cannot express it in Haskell, so here I'm using sort of like dependently typed Haskell. And it's commented out because it's not going to compile, at least yet. And the idea is that over here we have a proof that if we compose things in either direction, so if we go from A to B and then back to A, or if we go from B to A and back to B, in both cases we get just an identity function. However, in Haskell you have to actually check this yourself. You have to have like some sort of property check, or I don't know, some people just, you can just say, oh well, probably will work out. And like sometimes people come up with isomorphisms that are totally not isomorphisms. Yep.
Could you express this in Idris?
Yes. In fact, in Idris, you literally erase comments and you replace double colons with regular colons. And yeah, you pretty much get exactly what you want. You might want to, like over here, like this dot, it might be, I don't think that it's going to cause any problems. Like Idris will probably reduce it. But you might want to write it as from applied to 2x instead of function composition. But other than that, yeah, just exactly this. Oh, and by the way, Idris has a slightly different record syntax. So that's also going to factor in. In fact, in the standard libraries, there is a type called ISO that exposes all of this. And it exposes a lot of proofs of those isomorphisms. So you don't have to construct them yourself. Now, so why do we care about isomorphisms? There is a very incredibly obvious theorem, but it's incredibly obvious, but at the same time very powerful, in my opinion. Oh yeah. So if we know that A and B are isomorphic, and we have a pair of elements that map using that isomorphism, A1 and A2, and they map to B1 and B2, then we know that if those elements were equal in the original, like as A1 and A2, they're going to be equal as B1 and B2, and vice versa. And it's a, it might seem like a kind of like obvious result, but we'll see that it's actually kind of deep. Okay. So the proof is simple, right? If A1 if A1 is the same as A2, then we can apply our isomorphism in one direction by applying 2 to both sides, right? And since we just applied a function to 2 equal values, we're going to get 2 equal values again. But these two are exactly B1 and B2. Vice versa, we can start with B1 and B2. We can apply from to both sides, and we can get A1 equals A2. However, this proof will not work if the very first step that we do, we go from A1 equals A2 to 2A1 equals 2A2, right? If that transition doesn't work out, then this proof won't work, right? And it might seem like such an obvious statement, right? Like if 2 things are equal and we apply a function to them, then we're going to get equal results, right? Now, it is true when it comes to observational equality, meaning that if things were equal observationally, meaning that for every property that we observe about them, they appear to be equal, then if we apply a function to those values, then we're again going to see that they're equal. However, you can sort of see that it's kind of built into this definition, because here we say that it's not exactly right, but you can see that if A is the same as B, right, it says that for any P, where you can think of P as a function, P of A is the same as P of B. Now, like a slight caveat here is that P, we define it as a property that returns like a truth value, true or false. But, it's also a function, right? So almost built in. However, in Haskell, right, the standard equality in the standard library is totally broken in that regard. So sort of like the standard example is floating point numbers, where how many of you are familiar with this example? All right, pretty good. So basically, when it comes to floating point numbers, like float and doubles, I'm actually not entirely sure how they're called in Haskell, but whatever. It turns out that there are 2 different zeros, a +0 and a -0. And if you compare them, like if you check +0 equals -0, you will find that the standard equality operator returns true. However, if you apply this function to it, which is like 1 over x in comparison with 0, in one case 1 over x is going to be +infinity, in the other case it's going to be -infinity. And so you will be able to distinguish between the two.
On that, in the ecosystem, there are some bugs in the standard stuff that you would use related to those plus and minus. So that ends up being relevant.
Yeah, and another thing about floating point numbers, which even fewer people know, is that there are a lot of, there are not a number values, right? None. But there are a lot of them. Like, there are probably at least 2 to the power of like 50 of them. So you can actually store information in your nans and pass it around, which is pretty crazy. And I heard that some people actually do that. They actually do that. All right, so now, as we've talked, I give you this theorem, right? Equality preservation. Well, if equality is preserved, so is the number of inhabitants, right? Because equal things map to equal things, different things map to different things by isomorphisms, which means that if we want to count the number of inhabitants of a type, we can just transform it using isomorphisms to something that is much, much simpler, and then we can calculates the number of inhabitants, and will know that the original type also had the same number of inhabitants. So let's take a look at a couple very simple isomorphisms. Well, the first one is just, it's kind of like called unit introduction. And the idea is that if we have a value, we can create a tuple with a unit to the left side or the right side, and the number of inhabitants is going to be the same. Now, we'll see that this is kind of like actually a pretty deep result, even though it appears very, very simple. Similarly, if we want to, we can exchange things in a tuple. And by the way, let's think back to the counting, right? Remember we talked about how the number of inhabitants of a tuple is the number of inhabitants of each component multiplied, right? The number of inhabitants of unit is 1, and so this works out, right? So we have on one side, we have 1 multiplied by a, and on the other hand, side we have just a, which are the same. Now you can also commute tuples, and you also have associativity of sorts, right? Normally, when you think about associativity, I mean, I don't know what's your like kind of background, but if you are like maybe you're do a lot of category series, and then he knows that associativity is not just about monoids, right? Yeah, let's go to the next one. So, right, but like if you look at this, what does this remind you of, right? And I already spoiled it for you, but still, right? It reminds you of monoids, right? Pretty much. And we'll see that it's actually a much, much richer structure than just monoids. Okay, so are all of you familiar with void in Haskell? Like, who isn't familiar? Could you raise your hand? Okay, so in Haskell, let's see, who isn't familiar with void in Haskell and with nothing in Scala? Okay, so in Haskell and Scala, there is a type that is completely uninhabited, meaning that there are no values of that type.
Can you write it quickly on the board? The people on the right might not be able to see, but easiest definition.
Easiest definition?
Yeah, just data void, right? And in Scala, it's sort of like defined by the data void. Right, that's all you do. Basically, you declare a new type constructor, but you don't give it any data constructors. So the only way to, quote unquote, construct a value is by, like returning undefined, which is not allowed in our pure and total len for now. Actually, is not allowed for the rest of the stock. So. The first one is kind of like, think of it, so void is a type with no inhabitants, right? So think of it as 0. And you can fairly, now another thing to know about is that you need to know about void is that you can always dismiss a case if you have a void in it, meaning that if somebody gives you a void, you know that they lied. And so you can call them out. You can say, that's absurd. You lied. And so you basically, in Haskell, you can say, absurd, give it a value of void, and it's going to return any type possible, right? And the idea is that you're basically dismissing the case. You're saying, no, that's absurd. You couldn't have possibly passed me a value because this type has no type data constructors, right? And so I don't have it on the slides, but in the first case, you would pattern match on that either. And in case you get a void, you just dismiss it. You say, no, that's absurd. And in case you get an A, you return it, right? And so that allows you to write the first isomorphism. Yep.
So
void is what?
Well, that's a very
It's isomorphic.
that's kind of like a tricky statement, but like it depends on what you mean by bottom. But like if you mean the type, like I would say that void is a type of bottom, right? In some sense. However, you know, like you can use bottom in Haskell, right? You can use undefined for any type. So I don't know. I wouldn't say necessarily say that. Okay. Now turns out, yeah.
I don't know about bottom, but is it the same as unit in Scala or no?
It's the same as in nothing.
So yeah, you can think of void as nothing in Scala, and of undefined as, well, I guess like sys.error, and or like throw exception, and of absurd as, well, if you have a value of type nothing in Scala, you can just upcast it to any other value. So you kind of like get absurd for free. Okay, and well, it turns out that similarly, you know, like you can commute things, and it's fairly simple, right? You just pattern match and returns the opposite case, and you can reassociate things. This one is a little bit more tricky because people normally do not write this kind of stuff, right? But once again, we talked how the number of inhabitants of either is the sum of both components, right? In the first case, we have void, the number of inhabitants of void plus a and a, right? While the number of inhabitants of void is 0. So on one side we have 0 plus a, on the other side we have a. And here we have a plus b, b plus a plus b plus c, and a plus b plus c. Okay, let's go. All right, functions. Now, in functions, there's a little bit trickier, but basically a lot of useful isomorphisms, and most of you should be familiar with currying, right? We basically take a function that takes 2 arguments, and we produce a function that takes only 1 argument, but that is a tuple of those 2. I guess we don't have it on the board, but it's going to be later in the exercises. Okay, so we also have isomorphisms between functions that take unit and return some type A and z type A, right? So basically it's like unit introduction on the left. And we can also introduce any type on the left as well, as long as the right side is unit. And the idea is that this one is a little bit tricky, but think of it this way. What kind of things can you observe about a function that takes an a and returns a unit? Nothing, right? Because like even if you give it an argument, all you're going to get back is a unit. So you don't actually see like anything about it. It's just like all of the values of this type are going to be indistinguishable. You might have a function that does some weird stuff inside, like, you know, if you're dealing with Haskell, you obviously can do like unsafe perform IO. I would not recommend that. But, or you could be computing something really complex and then discarding that and returning a unit, right? But you cannot distinguish between those. Yep.
So I'm slightly confused. Before we said that the number of implementation of a function is given by e to the 8th power, right?
Yes.
So what about functions that go to nothing or void?
That's a very good question. We will talk about that. There is a problem there with functions that have to be careful, let's just say. Because there are certain corner cases there. Let's just say that 0 is kind of special because, well, we'll see. Okay, let's go to the next slide. Right, so, yeah.
I'm just going to attempt to answer the question. The idea is that if it's b to the a, then 0 to any power is going to be 0, right? And so,
Except 0 to the power of 0, which is 1. So that's what that's like one special case that you have to be aware of, and you have to be careful about that, right? So it's a to the power of b, and 0 to any power except 0 is 0. Furthermore, a to any power a to the power of 0 is 1 except when a is 0, right? So in both cases you need to to pay special attention.
Does that mean that the function from void to void is meaningful?
Yes, it's identity. That's the only one you can.
You can serve exactly one thing. That is void.
Yeah. All right. So we're going to take by this point, it's probably not a leap of faith anymore, but it's more like, well, that's an obvious thing to do, right? We're just going to replace every occurrence of void with 0, every occurrence of unit with 1, every occurrence of tuple with multiplication, and so on. The only leap of faith that I want you to take is to replace functions with b to the power of a. I mean, we sort of talked about it, but still, that's kind of still might be a little bit tricky. And so, for example, if we have an iso between either void or like this expression, right? We are going to rewrite it like this. Take a look and to understand what exactly we're doing here. All right, and so now I replaced in every single signature. I replaced things according to our table before. And what do you see here? Like, what does this look to you like? Is it like familiar?
Why are we using squiggly equals?
Squiggly equals means isomorphic.
Oh, yeah.
Yep.
Yeah, the isomorphisms for a category with product and Pillmore.
True. Anything? Yes, that's one way to look at it. Is there any other way to look at it?
like the loss.
Oh, could you? Kind of.
The laws of arithmetic.
Yes, the laws of arithmetic. Remember high school or like I guess middle school? I don't know exactly, but yes, that's exactly right. It looks. Remember, like 1 multiplied by a is a. Obvious stuff, right? But it is kind of like part of the arithmetic. Or like a multiplied by b multiplied by c is the same as a I mean, people normally don't talk about associativity when they talk about arithmetic, but you could. You kind of like have to, otherwise it's not going to work. Yeah.
I feel like you might be getting to this. I don't want to derail you.
Yeah.
If you're wondering why distributivity is on there, we'll get to it as an exercise.
Yes.
We got that part.
So, yeah, and I sort of skipped some things here. I mean, didn't skip some, but it's not complete table, right? There are more axioms of arithmetic than what we have on the board, and furthermore, arithmetic has negation and also like division, and we don't really have that on the slides, right? Yep.
Okay, so I can understand P is product, but what does the C stand for? Like, wouldn't that be like addition? Like,
Oh, so this is like C? You mean like the letter C?
left hand C. Yeah. Why
Oh. Okay, so one is products, the other is co-products.
Co-product, okay.
But I sort of like, I left them as P and C so that, to keep it a secret. Yeah.
Is this a ring?
It is a semi-ring, and it also has powers, so I'm not entirely sure. But it is definitely, the problem is, yeah, it is a semi-ring, but then it also has like powers, so not 100% sure what it is exactly. I mean, I guess it was semi-rings, you already get powers, right? But there are extra laws.
Yeah, so it's integer powers versus, or natural number powers versus powers within the ring.
Yeah.
Yeah. Oh, right. Yeah, exactly. So the difference is that, yeah, in a semi-ring, you have powers, right? But the problem is that those are powers where it's like a to the power of n, where n is a natural number. Whereas here, we also allow a to the power of b, where b is an element of that semi-ring. Any other? Yeah.
I don't understand why it's left unit. I expected that the 0 would be 1, but it wouldn't.
Oh. So left unit for coproducts, right, is 0 because, well, it's, if you think of it as addition, then the unit of addition is 0, right? What number, if you have x plus a equals x, then x must be 0, right? And in the slides before, it was a void there. So void maps to 0.
Because it's left unit. If it was left void, I would.
Oh, right. Okay, for those who are sort of coming from Scala, unit here means not just, it's not unit in Scala. Yeah, it's more like the neutral element of this operation. Or like empty, empty value. Okay, let's go to the next one. Okay, now here are a couple exercises, and we're actually going to give you a few minutes to think about those. So the first one is distributivity. The second one is tricky. Actually, that's one case which works out, right? Because I think that I might have misled you, a little bit there. But a to the power of 0 is 1 for any a. It's in the other direction that there are some peculiar things going on. This is called pairing, but you can see that like in this expression, it's basically like if you have an exponent and you have a sum in that exponent, then you can like separate the two terms. Okay, so you can spend a few minutes to convince yourself that these are true. I would suggest taking out a piece of paper and like figuring out how, or like in code, how those work. Actually, let's keep it. Is it mine?
No, or I don't know. Probably it's not mine. This is mine.
So we're taking like a 4-minute break. I'm going to get some coffee.
Yes. Right. Because we use prop. I think because we don't have any like fixity going on here, it's just easier to represent that without having to. Okay. Yeah.
On the intro of void, is it kind of like, since void is the additional object and it creates any one thing, it's almost like, is that true? And second, it's almost like almost acting like a selector where you're going to pick any one
Yes. Yeah. Actually, it's a consequence of initiality that says that there's one unique morphism from any initial object to any other element. So you could view it as a distinguisher or a classifier in some sense. Yeah. Yeah. So when we talk about A, we can also talk about the unique function from an initial object to A. When we talk about A, we can talk about the initial function from an initial object to A. Right? And that characterizes A. And depending on where you are, you actually get some pretty interesting results when you look at like functions to any, say, set from an initial object or like a sort of distinguished special kind of object, like a single point set to my A, which totally characterizes my A. And we're going to see exactly how that factors in here when we start talking about the Yoneda lemma. It's the empty set. So there's a table here, which we can get to in just a sec when Alex comes back. Yeah, initial objects are not super interesting for the remainder of the talk. It's actually it's a problem with working in category theory where small and concrete categories actually have relatively uninteresting initial objects. So your mental model for a lot of the initiality and terminality stuff can really just be either, like a singleton or something simple like that.
A singleton for the terminal, I'm basically picking an indexing of one or
yes.
As the initial.
Exactly. For instance, one of the things that I didn't include on these slides is, what is it? Actually, no, never mind, I did. We'll get to it. I have a whole bunch of interesting consequences. Yes?
In the beginning we said that functions will terminate, and because of that, in the beginning we said that the functions will terminate, and because of that, bottom would be included. Right. So when Alex said, think of void as the type of unit, I was kind of getting ahead of myself. Undefined or an infinitely recursing non-terminating loop, or or like throwing a system error in Scala, for example. Those are examples of values of bottom, which never terminate, so they just don't exist. Right? Yeah. And then we introduced void.
Sorry.
And then we introduced void.
What? Oh yeah, void. Void is, yeah, you said void. So Haskell's void is the type of non-terminating values, basically. So it doesn't exist because you can't construct a value of that type. Right. So we're not allowing it, but we can allow the type, right? So when we say 0 to A, we're saying, we can't introduce anything, so we just have like const A. And whatever is given as the value in heavy quotations of void is just forgotten. We never construct it, we never consider it. Yeah. This over to you. Yeah? Yeah. Since we're going to be...
Oh, I'm not going to be talking much.
Yeah. Okay. Your lapel. Right. For all A on which one?
Yeah, you can't just be like, I'm going to be one. Like,
for what?
For intro to void, we're assuming for all A.
Yeah. Well, actually, we can.
Like you can define this function, but
Wait.
I have no idea how this one works, right?
Yeah, it works. And you handle that.
So, the for example, you can use a third. Okay. And that's the one something that we use here. And in Scala, you can no, in Scala, you can just, in Scala, the way is nothing, right? So you can just offcast. Right? So you take value type nothing, and you just return that value. And it's going to automatically offcast any type. So any type. It's not shitty. We're just using the fact that nothing is both the bottom or the least. So there's a lower bound of subtyping lattice. I don't know what lattice is going to talk about. What was that?
It's how about the function? How would you implement the function? You can take any time with plus any time for that anything. And that is interpretations and not just one.
Could do that sorry, an object, then learn an A, you just take the object and do as is of it.
But such functions is not just one.
Yes. There could be many of those. But ours is distinguishable. Think about identity in this case, right? There are many functions that's true of this sort, void to A. At least in principle, that could be the harmless stuff. But certainly in Scala, it's the opposite stuff. However, we cannot really observe anything about it. So think about our table distributions, right? What is this function? It's a table with no entry, but every entry has type A. So, and it's like an empty tuple, and where every component is type A, but really you don't have any components.
So it's nonsense.
No, it's not nonsense. It's just there's only one inhabitant, which is absurd. Or in Scala, I mean, that's the same way.
It's a pseudo inhabitant, right? It's not an actual
No,
inhabitant.
it is an inhabitant.
Well, then you'd be unit.
Yes, it is unit. It's not zero inhabitant. One.
Oh, okay. Okay. And it's isomorphic to units. Okay.
Yes.
Got it.
Yes. And the other intuition is think in terms of identity with indiscernibles, right? Can we distinguish, like, if somebody gave you two values of this type, right? I'm going to give you two functions, void to A, for 7A. How are you going to distinguish between the two? There are no properties you can check because you cannot pass the value of void to that function, right? So you cannot distinguish them. Now, the cool part is that if you think of for all, what is for all? It's like, it's a conjunction of every single case. What is the unit of conjunction? Like, if you have a conjunction, what is the natural element of conjunction? It's proof. It's like 1.
Alex.
So that's another way.
Alex, you need to log in. You have it.
Visualization of why, if a function has two arguments, A and B, that is B to the A, like what's the picture?
So the picture is, if it has two arguments.
Yeah, isn't that what exponentials? Isn't that what it is? Because you're saying if a function has two arguments, it's the cardinality is B to the A. Is that right?
All right, let's take bool for example.
Function from A to B, then the cardinality, the number of inhabitants of the type is B to the power of A. As long as they're not all polymorphic.
Oh, so I said wrong. So any function that goes from A to B.
Yes, A to B becomes B to the power of. Okay. Okay. Why? So my best picture is as the same of a function as a table with entries for every single possible argument.
Right.
Then for how many entries are going to be the table?
So if like A has 3 and B has 2, that should be 8. But if I take A was a single dot, that goes to 2, so that's 2, 4, 6. I get multiplication out here. Okay, that's not
So what might help you is that it's how many functions can be derived from that time, right? So if you pass in 1, right? And so let's say that you have 2 inhabitants of type B, right? True and false. So, and you have 2 inhabitants of type A. So if you pass in true, you can derive a function that then derives the true and the false from true. And you can have a function that derives, if you pass in false, you derive the true and the false. So that's 4 total functions, right?
So that's something that we multiplication for that one. So we gotta have something that's that's what I'm missing.
So with 3, let's say you take 2 arguments, right? So your first argument can have 3 different functions that produce the 3 possible inhabitants of B. And then your second argument can have 3 separate functions produce 3 of the possible inhabitants of B. So that's how you get B to the power of 2.
Right. So I drew a little picture. Maybe you can imagine this in your head. So say we have a Boolean right here, so it's either true or false, right? You have 2 cases. And you have a function from Boolean to any A. Then each case of Boolean, so for instance true, can map to every possible element of A. And same, false, can map to any element of A. Right? So in effect, you have A many, so T times A plus F times A many possibilities for the outcome of this function.
Well, T is 1 technically, because, no.
Right, no, this is what we can do, right? So this is one value, this is one value, so we can go A, wait.
The A multiplied by A.
Yeah, sorry, times, because it's a table.
That's the part that
Right, because the whole table is the function, not just the individual rows. Right? So you have the number of possible outcomes for true times the number of possible outcomes for false. A many times.
Yeah, that's a fun way to look at it. So consider a function from A to B. Now set A be the natural numbers. What you've got now is you've got the strings over alpha A. That was like the best way to do it.
Well, in the strings, because,
Yeah, in the strings.
I would recommend, so take this, right? We have a table. 1 entry for true, 1 entry for false. What is a table of 2 elements? It's a tuple. So we have a tuple with 2 values, A and A. 1 for true, 1 for false. Actually, let me switch to.
Here's the one for maybe, for example. Maybe of A, I'm calling it A sub k in the case where A has k many cases, is either nothing or just a value containing this type A sub k with k many cases. And then the table will look like nothing. We can map to B any way we want. And just will be the number of ways that A sub k maps to B, which is the multiplication of every case of A mapping to B. So we have n times B times A sub k times B, which is B to the n plus A sub k, which is the number of ways you can map a maybe for some given type A with k many cases. Right?
We can move on. Let's slow it down.
Okay. It's the table. The table is. Do you have the slides again? Okay.
Sorry.
Okay. Do you want a microphone? Or do you want to move on from this?
No, I got 2 microphones.
Oh wait, you did. Sorry, I forgot you had one.
And so, right. Let's actually get back to this slide and yeah. Yes. Just try to yeah, so exactly right. So you have like a type with 3 possible values, mapping to a type with 2 possible values, right? You need to draw a table, right? For every input, you need to produce a value of type bool, which means that you're going to have a table with 3 entries for every input, and every entry is going to be a bool. So you have a tuple of 3 bools. Make sense? And the tuple of 3 bools has 8 possible values. So you kind of like go, you sort of like start with functions, you make a table, then you make a tuple, and then you can figure it out. So that's, like, if I forget about these things, I usually think it's this way. I think, like, how many tables can I produce? Because, like, functions, sure, like in set series, they can be represented as a table. And so that's the, like, what we are going for here. Okay, and so this is kind of like the picture that I want you to have about what we are doing here. We are starting, and categories is kind of like separate in some sense. It's a generalization of everything here, but we started with types, and so far we saw that we started with types, we can go to natural numbers, right? But if you think of types as sets, then we've been constructing isomorphisms between different sets. And isomorphisms between different sets are actually, in some sense, they correspond to equalities of cardinalities of those sets. Right? And so there's a connection. And if you are familiar with Power correspondence, you know that there is a correspondence between like progress and proofs. But here we're looking at the correspondence between types, sets, natural numbers, and categorical concepts that generalize those. Right? Now I'm handing it off to you.
Okay. Yeah. So we work with this arithmetic a lot of the time, sort of intuitively. Like you have combinators like the either combinator, the maybe combinator, the bool combinator in Haskell, which sort of do this for you, right? If you want to consume an either of A, B and produce a C, then you would take a look at maybe an either combinator, and you can see that it's a pair of functions, A to C, B to C, which takes an either and produces a C, right? And okay, higher. Okay, yeah, and this produces a kind of like isomorphic result to maybe pattern matching on the either and producing a C. We work with this all the time. So what we want to do is really just build a foundation for the things that we've already been doing and understand how that type arithmetic actually translates into a foundational logic in terms of category theory, and actually prove some really interesting things as a result. Because not only can you take this to basic arithmetic, but you can start talking about what do universal quantifiers look like in, say, category theory? What do like higher quantifications look like? If you're familiar with the lens library, and you see for all f, functor f, what does that mean? Well, there is a categorical foundation for it. What do lenses mean? What do prisms mean? We're not going to get into that, but I might do it as an unconference if anyone wants to come see. It's beyond the scope of this talk, and I don't think we can get to it in 6 hours, but we can almost get there for the most part. So it turns out that a lot of this this arithmetic stems from a few very sort of not elementary but fundamental results in category theory, which we're going to build towards, and then do maybe a few formal proofs, which actually, you can map one-to-one with your Haskell understanding of things that you've probably already done before. Okay? So we're going to start with preliminary definitions. So if everyone's familiar with category theory in here, this might be a little bit boring for the first 10 slides or so. And then we get into some interesting stuff. I've tried peppering it with if you do know category theory, you might find some examples interesting. But for the most part, we're going to start from ground zero, and we're going to build all the way up to natural isomorphism. And then we're going to talk about categorification, how to turn set theoretic concepts into category theoretic concepts, and how to go the other way. And then we get to talk about this amazing result in category theory called the Yoneda lemma, and talk about different forms of that in our section on representability. And then we have a whole lot of examples to go through, so you guys can actually work them out yourselves and get the muscle memory in your fingers. And then if we have time, we can get to the slick versions of all these proofs by understanding what adjunctions look like, and actually compute a few adjunctions that we've already seen, actually. And then get to, hopefully, limits and co-limits, where it's a one-line proof for currying and pairing and all this other stuff. So we have a lot ahead of us. And we've got, 5 hours to do it? So, yes?
Is it possible to have a quick break before we get started?
Yes, good idea. We want to take a 10, 15 minute break every lunch at noon? Okay. Okay.
Start the next step.
Yeah.
Zero earlier after lunch.
Well, we can get into some preliminary definitions. I think everyone's familiar who's worked in Scala or in Haskell. They'll be familiar with the first few. And then when we start getting into the hairy stuff, we can break for lunch and come back refreshed.
Okay. 15 minutes into lunch and give you breaks. You guys are fine.
Yes. Is that okay with everyone? Yeah? I think that's good? Yes. Good.
Because you're my hair.
It's fine.
No, I was told.
Oh. Okay. And then we'll count. So, yeah, we get to count. We get to play Count Dracula here. All right. So, any mini course on category theory has to start with the definition of categories. Is everyone familiar with a category here? Yes, kind of? All right. So, a category, at a very high level, is a way of grouping structures. So we have a notion of structure, which is our category, and then we have a notion of ways that we can preserve structure by mapping between witnesses to that structure. So we have objects and morphisms between those objects which preserve the structure of the category. Each morphism, so just as an example, imagine sets and set functions. Whenever you have a set function and a set, that set function will map a set to a set. If you think about groups, if we're familiar with abstract algebra or monoids, then the objects of a category of monoids would be monoids and monoid homomorphisms, which preserve monoid structure, and same with groups. More abstractly, you can think about maybe posets, so partially ordered sets with a less than or equal sign, and morphisms in this would be pairs of elements that are, like A less than or equal to B, then there's a morphism from A to B, and you have transitivity, which preserves, the chain of poset relationships. In the same way, we have a more general notion in terms of composition here. So for any category, we can have objects of a structure, morphisms that preserve the structure, a way of composing those morphisms, a way of identifying an element, which is an identity morphism. And we always know the domain and the codomain. So you could say that a category includes the data of two functions which pick out an object from a morphism for its domain and codomain. Yes? Sorry, what? Oh, yes. Typo. X to X. Sorry. Yeah. So is everyone comfortable with that? Oh, it's 1x to x to, yeah.
May I ask, how does morphism category?
That depends on the category. So for instance, in the category of monoids, you have monoid homomorphisms, which are defined to be, for instance, if I have let's say I have like star for my action, for my monoid, and I want to turn it into something which has dot, then I have a morphism from star monoid to dot monoid if it satisfies that A star B is equal to the image of A dot the image of B. Or sorry, yeah, I'd have to write that out. But, sorry, the image of A star B is equal to the image of A dot the image of B. There, sorry. Yeah, so, I mean, it depends on the category. In the category of topological spaces, for instance, they have to be continuous functions. And you define continuous functions in such a way that they preserve topological data, right? So you have, almost by definition, that these morphisms are going to preserve structure if they're already in the category. The unique way in which they do that is dependent on the category that you specify. Yes?
Perhaps intuitively in the category of types, they're just functions that give a type and then it goes to another type and that stays in the same category.
Do types form a category? That's a question. Yes. So you can think of like, in the category of Haskell, heavy quotations. You have Haskell types and Haskell functions which take type to type. Right? To be differentiated from function types, which are not the same thing as morphisms in Haskell. Not quite, at least. So you have the following axioms for a category. You can always pick out, f from x to y has a composite with either the identity on x or the identity on y on either side, and that's just the same thing as saying f. So if I compose, post-compose the identity on y with application of f, then that's the same thing as just doing f. And if I pre-compose with the identity on x and apply f, then I just have f again. For any composable triple, we have associativity. So parentheses around, so if I have f, g, h, for example, and I have f from x to y, g from y to z, and h from z to w, then h post-composed with g composed with f in parentheses is the same thing as saying h composed g composed with f. Right? So we kind of built a little monoid here, right? So we have identities and we have composition and associative composition at that. So every category, in some sense, forms a monoid with respect to composition. Between any two objects of x and y in a category, we can talk about the collection of morphisms between x and y, which we call its Hom set or Hom object. In this case, I'll just say Hom sets because we're working in very set-like situations. So, and I tend to denote it by C of x and y, just because it's a little easier to know what category you're working in. If anyone's comfortable with this or uncomfortable with this, just raise your hand and we'll review again because I realize that notation's a bit of an issue sometimes. Yeah. So that's a category. Any questions? Any ambiguities? Yes? Right. Right. So it's not quite closed. If you think about composition and the one arrow serving as the identity as opposed to individual arrows, then this forms a kind of monoid. With respect to any one x, you're right. But with respect to just the identity morphism on anything else, it'll be a monoid.
Question.
Yes?
I was never really comfortable with where, like, the equations live, like, you know, saying that such and such part of the diagram computes.
Mm-hmm.
The definition of a category never mentions that.
Right, so that's a slightly more subtle topic. You have a notion of categories of diagrams, which, you know, when you're sort of doing a diagrammatic proof, you are actually implicitly taking a functor from, which we'll talk about, a functor from a diagram category mapped into my category of a specific shape, and then filling in the dots, kind of. It's very abstract. It's a lot of pretty pictures, which we can actually write out. But if you imagine like the shape of a commutative square with, you know, no data, just dots and arrows, kind of like a directed graph, that maps into my category, and my category fills in the x's and the y's and the f's. Then basically labeling the vertices and labeling the edges. Right, so we have examples. We've gone through set, top, pos, mon, and Hask to some degree. Now, the really big question is, why am I kidding about Hask? And can you answer that for yourself? We live in a fantasy world where Hask is a category, so we're just going to work with that axiomatically, though in general it is not. Yes?
What's the specific reason why, or is it beyond the scope?
Man, I need to look at the table again. There's lots of things that it's missing, and many of them are edge cases with bottom. For instance, it doesn't have arbitrary coproducts. It doesn't have, shoot, I don't remember the specifics, sorry.
So I believe Hask is a category, but it's not a very nice one. It's not the category we want it to be.
Right.
It's not a Cartesian closed category. It's what we want it to be.
Mm-hmm.
But I think it can be made any category as it is. It's just a grow.
It's like a category of domains or something if you really stretch things. But in general, I need to re-explore that bit. Yeah, so all of these, all the ones that we really talked about were examples of what we call concrete categories. So categories with, say, the ability to identify the Hom sets and the set of arrows, or the collection of arrows and the collection of objects with a set. And in this way, we'll understand concrete categories to be ones with a very specific functor into set. And that's all about where we're going to touch. Or that's about all that we're going to touch in terms of sizing issues. I will teach you, about what it means to be small, what it means to be locally small, and we can we use those in two parts of the optional section. But for the most part, we're working in a concrete category where we can just consider things as sets. Okay. There is an interesting kind of Russellian paradox, though, when you start talking about things bigger than concrete or small or locally small categories. Things like the category of categories produces a kind of Russellian paradox where you do have to start talking about edge cases and size. Doesn't really have much to do with our talk, though, thankfully. All right. So we know what a category is, and we have different classifications of categories based on size. Right? So we have concrete categories in the case where objects and morphisms are sets. Small if only the morphisms are sets. So the collection of all morphisms in this category. And locally small if between any two objects, x and y, you have only a set's worth of morphisms. Which isn't to say that the entire set of arrows is a set, just that we can say between any two objects there's a set. Yes?
So most of the categories that are sort of applicable to programming, how do they fall under? Are they mostly concrete or?
Mostly concrete, yeah. Concreteness basically says I can treat my category like set, the category of sets, modulo some structure. The really interesting categories are locally small and large categories. And in our case, the concrete and the at most small categories that we work in or are familiar with in our day-to-day is, models of types and models of hashs and models of sets and so on. Yes? Yes?
CSY, there's the Hom set?
Yes. The Hom set, so the set of arrows between any x and y.
Isn't that topological? Why would it not be a set?
It's not always a set.
So the set doesn't have to be a set?
Right, so this is beyond the scope of the course, but this is why this classification is important, because, for instance, in homotopy categories and more abstract categories like the category of categories, you don't have a set's worth of morphisms between any two objects, or at least you're not guaranteed to have one in general. Yes?
When you say concrete, do you mean the collection of objects is a set? Or
Yes.
do you mean each object looks like a set?
The collection of objects is a set.
So a concrete category then does not look like the category of sets. Collection of sets is not a set.
Right, but if the number of ways that you can characterize any single object is a set, then it does look set-like.
Just the figures.
Yes, yes. They're not exactly sets, you're right. But it's the fact that between any two objects of which there is a set's worth, and I have a set's worth of ways of describing those objects, that it looks like a set.
When would you not have a set of the object?
That last
Probably
one
just question.
the category of set itself.
Okay, how about the category, yeah, exactly, the category of sets, and the category of groups. All right, the set of all sets is not a set, famously. It's a class, right?
Small or locally small?
Small. Wait, no. Category of sets is locally small. No, small. It's small. Like 0 minutes left. Yeah, yeah. we're pretty much done with this hard stuff. Yeah, so set is small. Yeah.
Okay, I think that it's time to take a lunch break. It's 12 o'clock. So,
Yeah,
I'm back here in 1 hour.
I'm not particularly hungry, so if you want to ask questions, I'm here for the next 5 minutes.
We'll have